So for this video, we're going to be trying to understand entropy quantitatively, and then we're also going to introduce the idea of free energy and see where that gets us. So let's just retouch on some of the things that we'd already talked about. So we talked a little bit about entropy already, right? And we know that this is this idea of disorder or randomness that's present. And in general, we tend to think about it in this way, right? As this idea of disorder. We did talk about it, the fact that it's really based on microstates, right? And so there are more ways to be disordered than there are to be ordered. So typically there is this drive more probabilistic that we're going to have a disordered system. And so in general, systems tend towards greater disorder. And so we talked about the things that impacted it. And what we saw is, well, the state of matter was important, right? Gases just have a lot more disorder because they occupy a lot more space. There's a lot more ways that they can be arranged, whereas solids are very highly ordered because these things are all in very rigid positions relative to the other atoms. We also saw that the number of particles was important, right? That when we have fewer particles, we tend to have less disorder. When we have more particles, we've got more disorder. So again, those are just touching on some of the things that we already talked about. We also talked in the past about the first law of thermodynamics, right? This idea that energy can neither be created nor destroyed. Well, there's also a second law of thermodynamics. And what that says is, in a spontaneous process, the entropy of the universe increases. So I want to take a little bit of time here to sort of unpack that just a little bit. So when we talk about spontaneous, just in general terms, and you're not talking to chemists, well, spontaneous usually just means something that's impulsive or sudden, that kind of thing. In chemistry, it has a very different meaning, and we want to sort of recognize that explicitly. So in chemistry, the idea of spontaneous means that a reaction will occur without any external influence. Now, one of the things I really need to point out is this says nothing about when. So one of my good friends and graduate students always wanted to say, well, spontaneously, your hair should really be on fire. But as it turns out, kinetics won't let that happen. And so we'll get to kinetics a little bit more. But the idea is that, yeah, oxygen in your hair, they'll eventually react, but it will take a little while for that to happen under the conditions that we're currently sitting in. And so that gets us a little bit of what spontaneous means. So let's talk about the universe in this case. Well, in the chemistry context, the universe consists of two things: the system of things that we're studying, and then everything else that we call the surroundings. And we can represent it this way, where the delta S, the entropy change of the universe, is going to be equal to the change of the entropy of our system, plus the change in entropy of the surroundings, right? So the things that we're studying and everything else together, that makes everything in the entire universe. Okay, we're going to come back to that in a few moments. I need to do just a little bit of a side detour of how we try to understand entropy just a little bit more and quantify it. So we're really interested in this idea of quantifying disorder, and this gets us to this concept, or this W. So the equation that was understood or recognized is this equation right here by Boltzmann. And what it says is the entropy is equal to the Boltzmann's constant times the natural log of W. And that's just the number of energetically equivalent ways that we can arrange this. So this gets at the idea of microstates. So like, how many microstates do we actually have here? So that's how we identify it. And so if we have a temperature of 0 degrees, absolute zero, so 0 degrees Kelvin, not Celsius, then there's absolutely no movement. There's no randomness at all. Everything is exactly in its place. But as we start to increase the temperature, there's going to be a little bit of variety, and those things are going to be moving, and there's going to be disorder present. And that's in part how we get to that idea of joules per Kelvin, that we do actually have this relationship to temperature. And so more energy is actually spread out at lower temperatures when we put it in. That's not something we're going to focus on. And again, I wouldn't really stress about this. We're not going to be doing too much with this, but it's just sort of helpful to see where we're going. And so really what we're interested in this idea is, well, that the change in entropy, of course, is going to be equal to the entropy of our final state minus the entropy of our initial state. And what that ends up looking like in most chemical processes is something like this, that the change of entropy of our system is going to be equal to, well, the amount of entropy that we have in the products, our final state, minus the amount of entropy we have in our reactants. That's our initial state. And again, you might be looking at this and going, wow, this seems really familiar. If you start putting H's in there, all of a sudden that looks like our calculating the delta H of a reaction, right? Where we use enthalpy and we do the sum of the products minus the sum of reactants. And again, it is very similar for the exact same reasons. And so in this case, if delta S is greater than 0, that means we're having an increase in disorder, or that means we're less ordered. And if delta S is less than 0, that means that we actually have a decrease in disorder, or they're more ordered. Okay, and it's nice to think about it in terms of disorder because that way increase goes with a positive sign and decrease goes with a negative sign. So it keeps things aligned. So if you think in the context of disorder, that actually tends to work much better. Okay, so now let's see if we can take this out for a spin and do a little something with this. So let's consider this reaction where we've got potassium chlorate, and that will react and it'll form potassium chloride and oxygen. So I want you to take a few moments and just try to say, okay, well, what would I anticipate would be the sign of this? Okay, so think about it for a few moments. Okay, so hopefully you've got something in your brain. Okay, we'll get to that in just a second. And then what I'm going to ask you to do is also do the calculation for it, right? So it's often helpful to kind of have a sense of where we're going to go. And so anticipating what the answer is going to look like could be really useful. And then we want you to do it. Well, in order to actually do this, we need the values for those reactants and products. And so these are the values. So what I want you to do is pause the video for a few moments, answer these two questions on the D2L form, and then once you're ready, come back and start the video again. Okay, so hopefully you've had a chance to actually do that and get those things submitted. So now let's look at how we would do this, right? So when we are considering this particular reaction, we consider this first question. What we hopefully noticed here, when you're looking, is you notice that we have this gas being formed, right? And remember that change of state really factors into the change in entropy, particularly if there are gases involved, right? And so here we go from something that's a solid, that's completely ordered, and we go to something that now has a gas. And so that's going to be a really big impact. In this case, we're also going to a system that has more particles, right? We started with 2 units, we're going to the thing that has 5 units, and so that also sort of suggests that probably we're going to see an increase in that case. And so from these, we're going to really assume that there's going to be an increase, and so when we do this calculation, we'd expect to see a positive value. Again, just sort of having that in your mind is going to be really helpful for you to sort of be able to double check things. So then to do the quantitative piece, right, we're just going to take our equation. The delta S of the system is going to be equal to the delta S, sum of the delta S of the products minus the sum of delta S of the reactants. We're going to plug in our values. And when we put our units in, right, joules per mole K, we're going to see that mole in there. That's going to remind us that we need to multiply by the coefficient. And if I was being really good, I would actually write this as, this is 2 moles of potassium chloride. And then down here, 1 mole of potassium chloride, because this number only works for potassium chloride. It doesn't work for the other ones. And so here we can see that the equation right now, when we do that calculation, and hopefully you got this answer. So what you can do is, if you want, and you want a little bit of practice, you can pause this and do the similar questions on D2L, or you can keep going on this and cycle back to those questions before you submit it. Okay, so now let's look at how does the reaction actually affect the surroundings. And so let's go back to that equation, right? The delta S of the universe is equal to the delta S of the system plus the delta S of the surroundings. And so heat that's actually lost by the system, so enthalpy that's lost by the system, right, it's going to go to increase the entropy of the surroundings. Okay, so we're going to give off that heat. It's going to add to the disorder of all the surroundings. And the way that that's actually related is by this equation. So the delta S of the surroundings, the delta S of the surroundings is equal to the negative delta S of the system divided by T. Because again, remember, entropy was tied to temperature. And so we do need to account for the specific temperature that we're at. And so at constant pressure, so that's a little caveat, but most everything we do is at constant pressure. So at constant pressure, this will hold true. And so that's really nice. And essentially the example, right, is that, again, if we're giving off heat, so we've got a negative delta H, right, we're going to put that in. That's going to then give us a positive value over here, right? A positive value means that we're increasing the entropy of the surroundings. Okay, so let's see if we can then rewrite this to really focus on the system itself. So here we've got our equation. We'll move it over there. And we know that the delta S of the surroundings are really equal to the negative delta H of the system divided by temperature. So we can combine those two pieces right there. Okay. If we multiply through by negative T, we would then get an equation that looks like this. Okay. And it turns out that this negative T delta S of the universe is a really convenient idea. And so that actually gets its own name. We call that delta G. So the delta G, well, G represents Gibbs free energy. And this is essentially the energy that's available to do work. Okay. And I'll hopefully clarify that in just a little bit more. So if the second law of thermodynamics is delta S of the universe is greater than 0, means it's spontaneous, that means that delta G has to be negative in order for the system to be spontaneous. Negative means that it's going to give off energy, And as long as we have a negative value, it's going to be a spontaneous process. So we can use almost all that energy to do work and still end up with a net negative. So that's where the idea of this free energy comes from. It's the maximum amount of energy we could possibly get out of any sort of system, or the maximum amount of energy available to do work that we can get out of a system. So let's see if we can do just a little bit with this kind of conceptually and get some basic ideas from it. So let's make this table and let's consider this equation, right? So delta G, right? That's our question of whether or not things are spontaneous. That's going to be dependent on delta H. Remember, we said that things were typically favorable if we were exothermic, if we're giving off energy. And we can see that relationship here, right? Because we want delta G to be negative in order to be spontaneous. So if delta H is negative, that makes it more likely that delta G is going to be negative, and therefore the reaction is spontaneous. Similarly, delta S, we said before that tends to be favorable if we're gaining entropy. Gaining entropy means a positive delta S. So with that negative sign here, because temperature is always going to be positive because it's in Kelvin, then that would make this term negative. So again, we can see that what we talked about being favorable, well, what that means is that it's more likely to give us a negative delta G. So let's see if we can just look at some examples depending on if delta H and delta S are negative or positive, and what that might say about the spontaneity. So we'll look at a couple of cases, and I'll have you answer those questions on D2L. Okay, so let's consider the case where a reaction is exothermic and the product are more disordered. An example of that could be something like this reaction down here, 2 molecules of N2O forming N2 and O2. Well, would you expect that to be spontaneous at all temperatures, spontaneous only at low temperatures, only at high temperatures, or never spontaneous? So again, think about what exothermic means in terms of delta H. Think about what getting more disordered means in terms of delta S. And what does that say about the sign of delta G? And that should allow us to be able to answer that. Then for case 2, and each of these will be in D2L. So for case 2, if reaction is endothermic and its products are less disordered, what does that say? So again, go through that same process here. And then go through the case of, hey, if it's exothermic and the products are less disordered, what would that say? Would I be spontaneous at low temperatures, i.e. when T is really small? Would I be spontaneous at high temperatures when this is really large, or never spontaneous? Okay, so see if you can walk through those, pause the video, and then answer those questions on D2L and fill out that table. Okay, so hopefully you had a chance to do that and fill out the table and get a good sense of that. Let's just see if we can walk through it pretty quickly here. So again, for this case 1, right, we had exothermic, meaning delta H is negative. We were more disordered, meaning delta S is positive. So if this sign is negative, when we put in a delta S, this minus T delta S is going to be negative. So together, delta G has to always be negative at any temperature. So we'd say this should be spontaneous at all temperatures. So this should be a reaction that very readily happens. If, on the other hand, we considered this situation where we had delta H was positive because it says this was endothermic, and we're getting a less disordered system, okay, so a more ordered, so that less disordered means the S is negative, so we put that delta S in here, and that's going to give us a positive term here. The delta H itself is positive, so delta G should always be positive. And so this is a process that would never be spontaneous. We wouldn't expect it to just happen on its own without external influence. And then in our last case, we had this example here where delta H was negative because it was exothermic, but the products are less disordered. And so the delta S is going to be negative as well. And so in that case, this is most likely to be spontaneous, to have a negative value of delta G when when T is low. Because when T is low, right, this term is pretty small. It's not going to have a big impact. So really, the sign of delta H is what matters at low temperatures. And so an example of this is if we have liquid freezing, right? So that's something that gives off energy and the system becomes less disordered. That only happens at low temperatures. And so as you're filling out that table, hopefully you got a table that looked a little bit something like this. And so when we think about how we could calculate delta G, which we're not really going to do, but I just kind of want to set this up. Well, we know delta G equals delta H minus T delta S. So we've seen how that can work. So for our reaction, that would take place. And we know how to figure out delta S and delta H of the reaction from the sum of the products minus reactants. There's also another way that we can do that. We can use the delta G of formations. We'll talk about this just a little bit more. And essentially, it follows that same kind of process. So we'd have to look up these values in a table somewhere in an appendix of the book or elsewhere. And these things are really going to be more the focus of the next class. I just sort of wanted to set up for that. So anyways, take a few moments, finish off any of the questions you haven't done on D2L, and we'll see you guys in class.